Welcome and hello. This is a video exercise in the HEC RAS controller. I'm going to be doing a steady flow calibration exercise in this video. Right, so let's go ahead and get started. We have a HEC RAS. We're going to build that out, and we're going to be calibrating the Manning's N coefficient. This is going to be a relatively simple model and simple calibration, but we're going to be demonstrating the use of the HEC RAS controller. So if you haven't already, let's go File, New Project, and then navigate to where we want to save the project. Okay, so that's the directory I want to save it to. I'll just call it project.prj and OK. I'm going to be using US customary units, edit geometric data, and down here I'm going to sketch out a river reach. So just boom, one single line segment there will be sufficient. I'm only going to have two cross sections, so we're going to keep things real simple here on the geometry. We'll call it river A, reach 1, and then click on the cross section button. Options, add a new cross section. I'm going to add our first cross section down at the bottom of the reach, which is river station 0. Now I'm going to paste in my station elevation data. So over here on the right, this is the cross section. Real simple, just invert Thalweg here at 220. I'm going to just type in some other data. So the downstream distance is 0. I'm going to go with a Manning's N of 0.02. We know that's lower than typical, but I'll explain the reasoning for that in just a moment. And then I'm going to say that the main channel is the entire cross section. So for the bank stations, that's going to be the ends of the cross section, which is cross section station 0 on the left and 70 on the right. Okay, so I'll click Apply Data, and then let's make a copy. As far as this Manning's N value, I should probably mention that we're going to be calibrating this particular variable, and we don't know what it is yet. So what I plan to do is test a number of Manning's N values, and then compare the water surface elevation, a few different flow rates using different Manning's N values, and then calculating an error for the observed versus the calculated, and whichever Manning's N value returns the lowest error, then that will be the presumed correct Manning's N value. All right, so I'm going to make a copy of this cross section for the upstream cross section. So that's going to be options, copy current cross section, same river, same reach, and 100 feet upstream. Click OK. So I'm going to update my elevations. I'm going to go options, adjust elevation, and then let's just go 0.1. So it's a 0.1% slope. And I also need to update the distance to the next downstream cross section. Okay, that's good. Apply data. Let's just double check that we have a slope, and we do, so that looks good. I understand there are a number of other options for getting creative and complicated with the Manning's N coefficient, but like I mentioned earlier, this is a very simple calibration just to demonstrate the use of the HEC RAS controller. So some of those additional details and complexities could involve horizontal variation within the N value, vertical variation within the N value. And then also if we click on unsteady flow and then options, there's also flow roughness factors and seasonal roughness factors, all of which we're not going to touch in this video. All right, so just wanted to point that out. I am aware of all the details that can go into calibrating the Manning's N value to get it just right for your geometry. In the geometric data editor, I'm going to go File, Save Data. I'm just going to call this base for our base case. And boom, we're now done with our geometry data. I'm going to just continue with the model building process here in HEC RAS before we jump over to the Visual Basic code. All right, so for the steady flow data, I'm going to have 3 separate flow profiles, and then those flow rates are going to be 200 CFS, 700 CFS, and 1300 CFS. I also need to add a boundary condition for the downstream. Let's go with just the normal depth as our option, and then use the longitudinal slope of the channel to approximate the slope of the hydraulic grade line, or the energy grade line. I'll click OK. And we also need to save the steady flow data. So File, Save Flow Data. I'll call that base. Okay, that's good. Next, let's create a plan, run it, look at some results, and then head over to Excel. So click on Run Steady Flow Analysis. All right, and let's go File, Save the plan, call it Base, short ID, same thing, call it Base. So we have plan name, the short ID, and then geometry file and steady flow file. We're going to assume subcritical flow. That's good. So let's compute, and boom, we're done in just a couple seconds. All right, let's check out some of our results here. Now, let's take a look at the cross section first. I like to do that. This right here is the cross section at River Station 100. Let's check out River Station 0. I'm going to be using River Station 0, this cross section right here, for this particular exercise, but we could change the Manning's end value at any cross section and calibrate for that particular cross section. I'm also going to add in the additional profiles because I'm only seeing one profile. Select all, click OK. All right, here we go. Cool. So PF1, this is our 200 CFS flow rate. PF2, this is the water surface elevation at our 700 CFS flow rate. And then finally, PF3 up here, this is the water surface elevation for our 1300 CFS flow rate. That's the third profile. Now, these water surface profiles are fairly low compared to some of the others that we're going to see, because this is going to 0.02 is sort of on the lower end of our Manning's end roughness coefficient. If we increase that Manning's end roughness coefficient, we're going to have higher water surface elevations. All right, so let's take a look at the actual numbers real quick. I'm going to go View and then Profile Summary Table. And then, yeah, this standard one table is enough. We have the water surface elevation numbers in this column right here. We're interested in the River Station 0. So reach 1, River Station 0, these bottom three rows of data specifically are water surface elevation for PF1, PF2, and PF3. 221.83, 223.79, 225.35. All right, let's head over to Excel finally. And what I'm going to paste in here is the start of the table that I'm going to be using for this analysis. What we're going to be doing is looking at the water surface elevations in feet, River Station 0. And we have our three different flow rates in columns 4, 5, and 6. And then we also have the observed data. So what we're going to have in this end column is the Manning's end. So say, for instance, we start with 0.02, and then after that 0.03, or we 0.021, 0.022, and so on. And for each of these calculations, we're going to record the water surface elevation for these three flow rates, the three profiles that we're going to be using. So in the case of 200 CFS, that'd be 221.83. Let's go back to Excel. 221.83 for 700 CFS. It's going to be 223.79. So 223.79. And then for the highest flow rate, 1500 CFS, 225.35. And boom. All right. I'm going to center justify my data here, and I'm also going to round. Okay, so we'll go with the Manning's end value to display 3 decimal places there. That looks good. And then on this far right column, this column 8, this is where we're going to calculate the error between the actual calculated water surface elevations versus the observed data. So this row 6 here is observed data for water surface elevations at these three separate flow rates. So the equation that I'm going to be using for this calibration is a root sum squared. There may be a quick way to do it, but I'm just going to write the equation myself. So 2.9511 is the calculation. That is the result of basically the square root of the sum of the squares between the calculated and the observed values. So you can check out the formula right up here in the formula bar. Of course, this is using R1C1 notation. So if you're not used to that cell referencing style, then hopefully it's not too hard to understand. All right, so that is the process. What we're going to do is now writing the VBA code, or I'll paste it in and explain what I did. But we're going to be running HEC RAS multiple times, once for each unique Manning's end value. We're going to change it. Well, first we're going to update the geometry file with the next Manning's end value, run the simulation, record the results, calculate the error, repeat that process for a wide range of Manning's end values, and then determine which has the lowest error. That will be our calibration process for this particular exercise. All right, so I'm going to just delete all this data for now. That's all going to be done through the subroutine. And then we can also just kind of close that up there. I'm going to click on Developer Visual Basic. And then here is the controller file that I'm working in. I'm going to double click on sheet 1 and then paste in the code that I have. It's about 150 lines, but it's organized in such a way that I think is fairly easy to understand. First, what we have is our main function. What it's going to do is define the Manning's n minimum and maximum, and then run this loop and compute each Manning n value one at a time. Before that, we have some data that's initialized, but we'll talk about that. And then this RAS compute subroutine, that's going to actually run the HEC RAS compute through the HEC RAS controller. So this is where we create the HEC RAS controller object. This is where we open the project, and then we perform the compute right on this line right here. And then finally, after that, for our three different flow profiles, we're going to get the water surface elevation, round the water surface elevation, and then print the water surface elevation. And then after that loop of all of our three different flows, we're going to calculate the air and print that to the worksheet. This calc air function right here is just right here. I just felt like it made sense to write a quick little function so none of my subroutines or functions were, more than 50 lines. Try to keep things easily readable that way. So calc air is the name of that function. It's going to return this air rounded to 4 decimal places. Here is that same function that I had pasted into that column 8. Here are the 6 different variables. The observed variables are going to always be on that row 6, and then the actual variable from the specific Manning's n is going to be on a variable row, which is going to increment with each Manning n. Ultimately, that's returned up here, and then we're going to print it into our column 8 for that particular row. Let's see what else. Okay, so I have a test function. Don't worry about that. That was just me doing some testing. And then update n. All right, so update n, this subroutine is going to open up the geometry file, and it's going to be passed the new Manning's n, and then it's going to update that Manning's n value for both of the cross sections with whatever value is passed in. So let's take a look at that geometry file just to confirm that the line number is correct. So here is my HEC-RAS project. I'm going to go project.g01, that's the geometry. Open up that file in a text editor, and here is that file. So the Manning's n value is right here. So let's see, this is the first cross section. That's why it's node type ID 1, and that's River Station 100. And then this block of code right here is our cross section data at River Station 0, because we have another 1 here for the cross section, and the river station is 0. All right, so what I'm seeing here is 0.02 is the Manning's n roughness coefficient associated with the main channel at that river station 100 cross section, and again 0.02 is Manning's n at cross section station 0. It looks like that is occurring on line 16 and line 27. So that is what I expected it to be. I'll close this file for the time being and then return to just make sure 16 and 27. Yeah, it's 0 base. So what we're doing here is our original line is going to copy line 16. This index 15 refers to line 16. Then I'm going to create an updated line, which is going to be basically the same thing, but instead of 0.02, it's going to be whatever the Manning's n roughness value that's passed to this subroutine properly formatted. And when I say properly formatted, I mean it needs to occupy the 8 characters from 32 to 40 in that file, because it would be the 5th number that's used on a 8 character length numbering delimiter. So it looks like I'm printing it out right here in the intermediate window. I don't need to do that anymore. That's just sort of a debug task that I might forget to remove after having tested this. So we're going to close the file for input, and then we're going to reopen the file. In this line right here, what I'm doing is I'm going to loop through just lines 16 and 27. So yeah, again, I don't need the debug here. Sorry about that. And then I'm going to update my array of file lines with that line updated. And then at the very bottom, I'm going to update my steady flow file, just like it says. I'll open up that same file, but for writing to, and then print all the same lines back to the same file, right? With our two new updated lines that contain our updated Manning N coefficient, right? So I'm going to scroll up to the very top and talk about a few more details here. What we're doing at the very beginning is setting the minimum Manning N value. This is something I could have built into the user interface and it could read in from the worksheet. I didn't do that, but 0.02, 0.06, that's going to be the minimum and maximum range of values that we're going to be using for Manning's N. And hopefully we'll see a local minimum of error values when testing this range. Otherwise, we may have to extend the range. This line right here is just to ensure that the maximum value is used in an upcoming for loop. Yeah, this for loop down here. And then here's the increment. So we're going to be stepping by 1,000th of a Manning N. Here, N is the Manning N variable. That's what we're going to initialize to the minimum. And then we're going to increment. So that's what this for loop is doing. It's starting at the minimum, it's going to the maximum, and it's going to increment by what we're setting to 0.001. Three flow rates are right here, 200, 700, and 1300. I just searched, and I'm not sure I'm actually even using this line, so I'm going to take it out. Sorry about that. Row results, we're going to initialize that at 6. I believe it actually starts at 7, but that's because I increment. Yeah, the results we're going to start at 7, but increment just before using it. All right, this block of code is going to represent the different variables that are required for extracting the water surface elevation variable after the results have ran using one of the HEC RAS controller procedures. So our river ID is 1, our reach ID is 1, node ID is 2 because we're interested in the cross section at river station 0 instead of 100. UPDN is not used for cross sections. Profile IDs, this is 1, 2, and 3 because that is associated with our PF1, PF2, and PF3 for the 3 different flow rates. And then we're going to loop through those 3 profiles when getting the results. So I think we kind of talked about everything now. Here's where we loop through the Manning N values we call the RAS compute. We increment the row results here. We print the Manning's N value to the worksheet right here. This is where we set the geometry file. Here's that function call to update N, or it's a subroutine call. Here is the new Manning's N. We create the HEC RAS controller. We compute the data. We run the simulation. And then we get the water surface elevation for all 3 of our flow profiles and record it. Okay, let's go ahead and see if this thing works. So I'm going to go ahead and save. And then let me pull this off to the side here. Let me also bring up the Excel so we can see this in action. I don't have a button pressed to invoke this subroutine, so I'm just going to run it straight from the menu here. I'm going to go run and run subroutine. So it looks like it's running right now. That is the first record right there, 0.02, 0.021 for Manning's N. And then this is the water surface elevation values. And then here is the air value over here. So the air start at 2.95, 2.76, 2.58, 2.39. You can see with each iteration, the error seems to be decreasing, and that's because the calculated water surface elevations here for all 3 profiles are getting closer to and approaching the actual observed water surface profiles. I'm going to go ahead and speed this up just so you guys don't have to wait as long. Okay, it looks like our air value has now dipped below 1, so we're only getting closer and closer. It looks like Manning's N value is going to be above 0.33. Above 0.033, 0.035. Okay, this is getting really low. We're still getting closer. Okay, that right there is the minimum, I think, because 0.0, yeah, it's starting to go up. So 0.038 is the closest Manning's N, and then the second closest Manning's N would be 0.039 because those are our 2 lowest errors. And I can't scroll down at the moment because it's still running, but I will do that when it's done running, and we can confirm that these are the 2 Manning N values that result in the lowest error, and hence the results of our calibration would be between 0.038 and 0.039. All right, so that finished up, And indeed, we do have a minimum right here at 0.038, 0.039. You can see the error continues to increase, and the last value is 0.06. So that error was just as high as where we started, basically at 0.023 or something, 0.022. In fact, let's go ahead and do a quick plot of Manning's N versus the error. Just out of curiosity, I kind of wanted to see what this might look like. So with these two ranges of values highlighted, I'm going to go up to Insert and then click on Charts XY Scatter. Okay, so very cool. We can see that that error is minimized right here at around 0.038. All right, very cool. Now, I'm going to go ahead and delete this data. We know that it's between 0.038 and 0.039. So one thing I want to just try to do here is modify the variables for n min to 0.038 and 0.039, and then change the increment to step by, instead of 1,000, 1/10,000th. And let's go ahead and run this just to get one more decimal place precision on the optimal Manning's N value. So I'll save that. One more thing I want to do here. Hold on, 0.0381. Yeah, I think this is going to just display. Let's add one more decimal place of display. So that's under number. And then here. Okay, cool. So I'm going to just delete that and save and then run. So 0.0380 is right there. Next will be 0.0381. Okay, so we're still decreasing. 0.1. Okay, so now we're going back up. So I believe this one right here, 0.0383, is our final calibrated Manning's N roughness coefficient. We'll let this continue playing out, but that is it for this exercise. What we did was create a simple 1D model in HEC-RAS, and we went to calibrate the Manning's N coefficient. We did that for 3 separate flow rates, which had observed stage data, and then wrote a script in VBA, utilized the HEC-RAS controller, ran the HEC-RAS routine multiple times for different Manning's N values, calculated the water surface elevation for these 3 different flow profiles, and then calculated the error, selected the Manning's N value with the lowest error.